So let's see some radiation data. So yeah, on this work, I will present some results we collected from a test vehicle we manufacture on the 10 to 80 nanometer FD-SOI from ST Microelectronics. A brief introduction. So the main motivation for this work is it's our next generation space grade processor that we are developed together with ESA, the GR765. I can be very brief on the description of the device because my colleague Magnus will give a talk at 5 about it. But basically, the GR765 it's an octa-core system on chip, fault tolerant. It is it has a dual ISA architecture, so RISC-V and Spark, and it is based on the 28 nanometer FD-SOI platform for space from ST Microelectronics. The objective of this work was to evaluate the performance of NOEL-V, of the NOEL-V processor core implemented on this technology for single event effects. A short introduction on the NOEL-V processor core. So it is the NOEL-V. It's a highly configurable core. It can be configured for 64 or 32-bit architecture. It has a 7-stage in-order pipeline that can be configured for dual issue or single issue use. Some of the features are late ALUs, branch units, dynamic prediction, and so on. It also has an L1 cache. That consists of separate instruction and data caches. It can be configured up to 4 ways with 16 kilobytes each. Has write buffer, is snooping for coherency, and so on. In terms of fault tolerance features, the processor uses the well-established features from the Leon processor line. So there is a very good heritage. And in terms of softwares, it leverages the software tool support from the RISC-V community and also our own software ecosystem. Because of the primary feature set, it can run complex OS like Linux and also within a virtual machine, and has AHB and XAI4 bus support. In terms of fault tolerance, a brief overview. So the main feature of the main focus for fault tolerance is to protect the memory blocks, the register file, and the caches using error correcting codes. So they are protected with a full single event correction and double record detection with a custom pattern scheme that I will show in the next slide. The main idea here is to deliver correct data locally without causing memory overheads, excess overheads. And also, this scheme also guarantees the detection of also 3 and 4 bits adjacent bit errors. The register file and the caches, they have a hardware scrubber built into the processor to avoid the error buildup, and that also removes the need of manual scrubbing and flushing and things like that. The processor has error counters and diagnostic interfaces where you can monitor events, and also you can do error injection. So the custom L1 cache scheme, it works over 32 bits with 8 bits with 8 check bits. So it follows the conventional BC8 protection 32 plus 7, where you can correct 1 bit and detect 2-bit errors. The main difference is that the top half of the check bits are also XORed with the other code word nibbles. That allows a simple parity check to detect events, and consequently that reduces, that shortens the critical path and allows increasing the maximum frequency. As I said, it guarantees the detection of 3 and 4 adjacent bit errors. That is important for heavy ion rich environments. And the corrections are done transparently in the cache controller. There is a built-in scrubber to avoid error buildups and error counters, as I mentioned before. So the device under test. So the device on the test doesn't, it has not only the NOEL-V core, it also has a Leon-V core together. They share resources inside the device. And the device is based on the 28 nanometer FD-SOI from ST Microelectronics for space. The platform has radiation hardened cells for single event effects. The technology has an intrinsic latch-up immunity in the SOI areas. And the platform is fully characterized up to 50 kilowatt. The idea is to prove the implementation on the target technology, and this device it was developed in a collaboration between ST Microelectronics and Geisler teams, and it was manufactured on a European supply chain. So the device under test, the test setup. So the device under test is quite simple. It consists of the two cores. They share the L1 cache. The ASIC also has on-chip memory, a small on-chip memory where the software is stored. And there is a SoC bridge to an FPGA from where we can have access to an external memory and also to do some monitoring. The test setup allows us to also play with the core voltage and the body biasing voltage from the library. So we can do some experiments by varying these supplies. And on the software level, this device is very simple. It's just one core, one unit of each processor. They don't work in parallel. They work one at a time. The device needs to be configured to operate either on NOEL-V or Leon-V. We did different tests, integer unit, where we basically fill in the entire memory, and we execute a simple matrix operations. Paranoia to exercise, it's a classical benchmark to exercise the floating point unit, and Stanford, which is a mix of different benchmarks. We looked for silent data corruption, single event function interrupts, and we also monitor status bits from different memories and processor events like hangs and traps. We did two experiments, one heavy ion campaign in Belgium and one proton campaign in Switzerland. And some of the results, in summary, we didn't observe any functional event. We didn't observe program failures. We didn't observe CEFIs. And all events detected in the memories, they were correctly by the fault tolerance features of the processor. We also didn't see any SEL-like events. This is just a plot of the cross-section per bit in arbitrary units. On the proton tests, we also didn't see any event. So the results were very similar to the heavy ion tests. Since we had more beam time, we were also able to do some different to test the device in different configurations. And the results were always the same. So the main conclusions, we managed to demonstrate the SE performance of the NOEL-V, and not only the NOEL-V but of the Leon-V processors on the target technology. In summary, all the flip-flops and the combinational logic in the device, they were hardened by the standard cells of the platform. Following the tape-out, we did several improvements on the processors, targeting the final version of the GR765 design. We didn't see any events, any functional events. We didn't see uncorrectable errors in the memories, and all events detected in the memories, they match with the expected cross-sections per bit for the technology, which reinforces that we didn't miss anything. Some SE rates estimations for the memories. I mean, based on the results collected, we can see we can expect and do some simulations. And for example, events on the L1 cache, we are talking about 790 events in a geo orbit, and that can be easily corrected with EDAC and scrubbing. So that's an overview. In case you have more, you have interest on the work, this same work was published in RADEX 2023. So the paper is available. It contains more information, and of course, I'm always open to talk about the topic. So thank you.